programs, right? So for those of you who came with some expectations based on the title but did not skim through the paper, you may be in for a surprise, because he defines probabilistic programs in a very, very restricted way. And I'll talk a bit about that. To those of you who actually skimmed the paper and or went through this, okay, well, to those of you who actually read the entire paper and were like, okay, I'm really excited to talk about Banach spaces and all these vector lattices, you may be disappointed because, well, I'll talk about that. My goal here today was really to make the paper less scary. So I organized a probabilistic programming meetup here in Toronto. We've had about 8 or 9 sort of meetups to date. In the last session, which was a few weeks ago now, we came across a paper which was looking at how to do actual inference in probabilistic programs, and this was one of the papers which was referenced there. So we didn't really go through this, and I think there's no real practical need to go through this unless you're sort of interested in, okay, where do some of these things, ideas originate, and what would be some of the, if you're a PL nerd, or if you're sort of, you really enjoy semantics, or if you're thinking, okay, well, how can I actually think about interpreting these statements in a different manner, then you may find this kind of cute and interesting. I certainly did. I also found it scary, right? This or very sort of sleep-inducing. I think that's the better word. It's seasoned enough to not be scared away, or either that or just some masochistic tendencies. But reading through this, I think I made multiple attempts, and I was joking around, but there's a kernel of truth there. I think in all of those events, there were portions, there are chunks of the paper that are just kept as black box, and I'm like, okay, I will trust your word for it that this is true. I'm not going to go through the steps because I don't have the time, and or I'm just tired, and you just put me to sleep. So my goal, however, was to focus on some of the, I think, conclusions, or some of the thoughts, or some of the thinking, or some of the ways that he's expressing semantics, and to perhaps make that a little less scary, to give a bit more of the intuition. And the paper actually does a really good job of it if you manage to live through and pass through the notational aspects of it, because there are chunks in there which actually explain very, very nicely what are some of the intuition behind these ideas. So we'll focus a bit more on that. I won't be going to the mathematical technical depth. Perhaps time permitting, and depending on the audience towards the end, we can have a bit more discussion about it, about various aspects. But I'll begin first by defining, what is he talking about when he's talking about probabilistic programs. And so one of the things is, I like having a bit of a discussion. It's nicer to just ask questions, so if at any moment you want to interrupt, go ahead and shout out. So he focuses on really a very sort of simple language. It's which makes the analysis easier, like with most papers. And it's sort of also a byproduct of the time at which it sort of came in, and or his history with programming languages. So it's a very sort of very imperative-looking, simple programming language. And he calls it probabilistic because it's non-deterministic, essentially, right? He calls it probabilistic because there's random assignment, there's some randomness there. And I think, Dexter Kozen, if you've read any of his sort of papers or books on analyzing algorithms, or any of the sort of complexity analysis stuff that he may have, or more in algorithm design, however, he focuses on, like, his idea is, okay, I'm going to focus on this principle, and the rest sort of just follows, so I'm not going to focus about that, right? And there's a kind of truth there, because probabilistic programs are really programs which are giving you non-determinism and giving you some control over that non-determinism. And once you introduce random numbers, well, you can create a whole bunch of other stuff from it, right? You just need some random primitives. And you can have one kind of random number generator, you can have 10 different kinds of random number generator. Doesn't really matter, you could have 10 modifiers on that, and blah, 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 you can sort of keep going. But he doesn't talk about that. Why? Because the analysis remains the same, right? And so there will be a lot of such things in the paper, which I hope some of you, if you have an interest in that, and who are sort of curious about it, like, okay, well, I want to actually see what some of the mathematical foundations which are being mentioned, or what are some underpinnings on which the intuition is standing. Then keep that in mind. I think that's a handy thing to remember. remember. Probabilistic programming, as you may or may not already be aware of, or if you have any sort of idea of it, you may be sort of thinking about, so in modern sort of parlance, it's true that you need some just sort of randomness, and it often is some non-deterministic program, and probabilistic programs or programming languages make it easier for you to express such uncertainty. But they go beyond, right? So in any modern probabilistic programming language, and you can compare sort of Church, Anglican, Venture, Buckaroo as a sort of library, Info.net, Stan, PyMC, you can sort of keep going, there's a whole bunch there. All of them have one very, very nice property, right? They will allow you to describe what your assumptions are. They will allow you to describe how you think the world works. So what some of your assumptions may be, you're saying, okay, well, I think the random process behind generating this data looks like you toss a coin, and then based on the coin, I may take another decision, and then based on that, I may say yes or no, right? And this may be something that you're sort of positing, or this is how you think some of these things are related. If you're observing data which is some stock market data, say, you may be positing that, okay, the variable which is tracking the price of, say, oil, has an influence and is correlated with the variable which is tracking the price or the stock prices of oil companies or things like that, right? And you can actually say that, oh, that relationship may be positively correlated in this way, and you can actually talk about that. So they allow you to express what you believe or what you assume, right? And these assumptions can be very sort of naive, or they can be very constraining, or they can be sort of, the non-informative assumption saying anything is possible and it's just uniform where there's no relation here, and tell me from the data. But that's sort of the important point, which is after having expressed whatever your assumptions are, and after having provided a data in some way, they allow you to do sort of backward reasoning, and that's sort of built into it, right? This process of known as inference, going from what is known to the unknown and actually finding an answer. So working backwards is an artifact of most probabilistic programming languages. Not so in this paper, right? This paper just says, okay, you have some random number generator, awesome, you are working in a probabilistic programming language. C is a probabilistic programming language, Fortran is a probabilistic programming language, blah, blah, blah. All of these things are probabilistic programming language. Why? Well, because the truth is that given that, you can actually write an inference engine, and you can actually do a whole bunch of stuff. He doesn't tell you how to do that. He doesn't even focus about that. It's like, well, it's possible, so who cares, right? We just focus on this analysis. So I think that's an important concept to keep in mind. But if you are interested in probabilistic programming in the sense of that which makes it easy for you to actually do backward reasoning, and for you to not have to write a specialized inference engine every time, then I invite you to the probabilistic programming meetup group, where we actually talk about those kind of systems which are a bit more on the application side, or even more on the theory side, and yeah. Okay, so they talk about a simple language, and I will actually restrict this even further for this presentation, right? So they have deterministic assignment, they have random assignment, and this is essentially the only stochastic thing that they have, right? So I can take a random number generator, get a value from it, and assign it to something. That's it. That makes my program probabilistic. And composition, so I can have one expression, and I can have another expression after that, one statement rather, and I can have another statement after that. So I can have a program which is a collection of statements. And conditionals, I have some ifs, and I have some way to repeat multiple times, recursion or while or whatever you want to do. The semantics of it, sort of, at least in terms of how you interpret it, seems to be mutation based. They also seem to be eager in some of the rotational. This is sort of almost assumed, it seems like. I don't know if switching strict eager versus lazy, or call by name versus value, would that have an impact on some of the notation that he has? But it seems to be pretty sort of C-specific. So I'm not saying that if you were to assume certain lazy semantics in the notation that he has, that analysis would go wrong. I don't know. I actually didn't try it, but it seems to be follow more sort of imperative style. Right. So, any questions so far? Cool. So in this, we're actually looking at a simpler language. There's only one type, which is Booleans, and I'll show some code associated with it. But we restrict ourselves to booleans, and I will actually kind of change some of the semantics and actually have numbers in there, but think of those as just primitives. You're not something, you're not supposed to tweak those a whole lot, or just take those as built-ins. And we just focus on limited number of variables, two. So one which is assigned, you can think of one which is assigned deterministically. This is just the input variable in some sense, and then others which you're modifying or something in some sense. We'll look at some code examples, but I'll look at a very restricted case and see how they define semantics. And we may have some primitive functions, double, add one, or identity or not, and things like that. So in this case, double and add one don't really make sense when you have booleans, which also speaks to I've corrected this, but what we have is identity and not, and certain others. We do a live coding session towards the end, so we get to play around with what the intuition is behind the second kind of semantics that he talks about. So he defines semantics in two ways, and if you are coming from a programming language sort of background, these are sort of the two breakdowns, general breakdowns, and within them they have sub-breakdowns as well. I'd always sort of, there is a distinction in how you define these, how you're defining what is operational semantics, what is denotational semantics. The time that I remember that distinction is often can be measured in like hours or minutes after I've read it. I'm like, oh, okay, that makes sense. And after that, that distinction sort of just goes away, and I can interpret operational semantics and I can interpret denotational semantics, but if I have to recall which one is which, it gets hard. But operational semantics usually are defined at a very sort of micro level in a very fuzzy way. Again, I'm trying to make sure that you guys can get sort of an intuition. And as you'll see here, he'll be defining an operational like semantics, which is going at the variable level. So every value of a variable, that's what he cares about, and he's tracking those values. He's tracking those values very, very explicitly. What he is drawing, which is similar to denotational semantics, he's looking at not the value, but really the characteristics of those values. So he's actually looking at just probabilities and looking at what probabilities get induced and seeing how various statements or expressions modify this probability space or mask. So the idea here, when he's giving the semantics, is that he says, okay, well, I can have some deterministic assignment, right, and I have some deterministic variables. Let's say that they are n in number, and because I have if then else, I have got while loops and things like that, and I have random assignment, and I can have random assignment in any one of these places, right? So if I've got random assignment sitting within a while loop, I could have countably sort of infinite times that I'm requesting a random number generator. So he's keeping a separate sort of lazy stream or a stack, infinite stack of just random number generating sort of values, which is just sitting there, right? And this can be multi-dimensional depending on how many random number generators you have, blah, blah, blah. You can think about that. And he's got this sort of space which is just dealing with the actual variables, and then goes entire stuff which is just random number values. And we'll go through what happens. So he says, okay, this is how I'm defining my program, and based on that, as I go through the steps, let's see how this state, how these variables, how these things get shuffled around, how these values rather get moved around. And that's how he's defining these, the first kind of semantics. So very, very specific. Right, so let's look at, he breaks it down into the syntactic cases, right? So simple assignment is just x1 is, say, some f of some set of variables. And like I said, I'm just saying that there is just one variable, right? So x1 is f of true. And he's saying, well, what happens to these values when this thing gets executed? What is the meaning of this thing, right? So when the compiler or the interpreter comes to this and this is the first step or this is the nth step, and it executes that, what happens? What changes, right? So he says, well, there's nothing random which is happening. So the infinite stack which is there of our random number generator values, they don't change. They just remain as is. I'm assigning a value, which is the result of a function evaluation, right? And so, and I'm assigning it to some variable, which is this x1. So what it does is, okay, well, what is the value which is associated with this x1 variable? In place of that, just put the value that you would get by evaluating this, which is what you would x1 becomes identity, sort of true, and if f is actually not, then x1 becomes false. And essentially that's what the operational semantics here would be. Right? So completely deterministic doesn't make any change. And you'll see the only sort of randomness which happens is the random assignment. And it's like, okay, well, what happens if you have a random assignment? I have a random assignment, so I need this f is actually saying, get me a number from a random number generator. Like, okay, well, where is that? That's away on this stack, so I'll use it, but I'll pop it from it because I don't want it to be reused, right? It's not very random. My random number generator is not very general or random if every time I'm giving the same answer. Now you can still model something, a very sort of twisted random number generator, which is just a point mass and giving 42 all the time by having just an infinite sequence of 42s, right? But you want to take it away because you've used it. Okay, so I popped it up from the stack and I'm putting it in the place where I had the variable which was x1. Right, so the same thing, the assignment semantics remain the same. The only thing which has changed is, well, how am I calculating the value? And the act of calculating that value pops it up from the stack because it's requesting it from the random number generator. Does that make sense?
Sorry, are you saying that a particular random value won't show up twice, or?
No, so I'm saying if I've, each call to a random number generator, if I'm interpreting it, is the equivalent of me popping up from that stack of infinite random number generator values.
Right.
So composition, well, do this and then do that, and that's basically it, right? So if I've got x1 is this, and then after that I've got x1 is this random number assignment, well, first do the first thing and then do the second thing, and that's basically all it's saying. Conditionals get interesting. So how do we read this? So just focus on sort of line by line, and we'll go from there. Yeah. The color? Oh, yeah, you are correct. Let me just try and change. Maybe I can even change the layout. That may help. Okay, that would help. Okay. Otherwise, let me see if I can just make it. That's not there. Yeah. Okay. So this line right here, right? So let's go line by line, and so it says if B, then S, L, T, else T, right? So have some condition, and if that condition is true, do something. If not, then do something else. Well, this is equivalent to if I have a condition, then do something, and if I don't have that condition, then do something else, right? And that's the second line, essentially. Break it up into those two cases. And I've broken it down, actually, in a way where he doesn't make that clear in semantics 1 necessarily. Well, he breaks it out into two cases. But he says, well, how am I testing for B, right? What would this B be if you're thinking about it? So I've got some sequence of steps, and suddenly I have some predicate which is coming in, right? This predicate has to be based on any one of the variables which are defined above. It has to be a consequence of that, right? It cannot be addressing any variable which is down below. I'm proceeding top down, right? So B is a function of all the A which I have up to date, right? So B can be seen as a function of everything which is above it, and that's how you model it. So he says, imagine B. B is saying if B is true, the condition of B being true can be seen equivalently as something existing in some set, as set membership, right? And what is that set? Well, that set is defined as a function based on all of the things above it. So let's be a bit more concrete here. We had x1 is saying not of true, so x1 is false, right? And if I say if B is x1, well, in this case, that x1 is a function of all the stuff above it, and the stuff above it is just x1, right? Or I could have, instead of B, I could have not of x1. I could have that as B. Well, it's just looking at all the stuff above it, and you're asking, well, is the stuff above it, does that induce B to be true? If it does, then do S. If it doesn't, then you're outside of that set and then do T, right? So if B was not x1, and x1 is say true for whatever reason, then what that means is all the stuff above it is inducing a state which is false. So you're outside of that set, which was capturing true. And so he just breaks it down like that, but there's nothing sort of magical happening as far as I could see. And he's just broken it down into those cases. He's like, a predicate can be seen as set membership. Ta-da. While loop, yeah.
Is that set membership like the set of all instructions that could appear before it that would result in a true expression, or?
It would be this, so he switches notation and actually uses notation which is, I think, more tuned to semantics too, because he says if f is in B, where B is more, I think, is part of the space that he's looking at. But concretely thinking about it, just let's see, if x1 is, if B is not x1, right? So when would this predicate be true? This predicate would be true if x1 is false, right? And so what is that set? That set is x1 equals false, is that set. So the set definition is a consequence of everything, which is in terms of everything above it, essentially.
Okay.
Right? So you can translate that in that sense.
Okay.
So then he goes to while loop. And while loop is, well, if B, then do S, and then continue repeating, essentially. Right? So if B, then what do? S, and also continue on and do while we do S, repeat it. Right? So there's a sense of recursion there. And that can be broken down further. If B, then S, and then again, if B, then while we do S. Right? So you could break it down into those two cases, which basically means I can unroll this loop, and I can unroll this loop n times, where n could be either omega sort of infinite, or it could be some finite step. Right? If it is something finite, then all I'm doing is unrolling this repeatedly n times. So what did we learn from composition? Just keep doing that multiple times, right? Do f and then do f, then do f, then do f. So it's f to the power n, where n is that number of steps, right? That's all you're doing. But if that loop never terminates, well, then it's undefined, and you give up, and there are no semantics associated with it. So that's it for semantics one. There's nothing else sort of going on there. Yeah.
I'm confused.
Yeah.
So let's say you replace x1 in this expression. You say if x1 then something. If you replace x1 with
In this conditional?
yeah
Okay.
with f of whatever,
Mm-hmm.
and this is somewhat probabilistic. If
Yeah.
you make rewriting it this way,
Mm-hmm.
if x1 then such and such, if not x1, it looks like almost like you executed x1 twice.
Oh,
If
okay.
it's probabilistic, then I would assume that I don't know, it's not a
No, no, no.
different value.
Right. So what I'm writing here is pseudo code. So he's looking at pseudocode, and mine is even like a pseudo version of it. Right. So the way to read this is not to say that I'm executing B twice. I've executed that function once, captured its value, and this is simply expressing that I'm referring to it.
Alright.
Yeah.
And the same balance for the one. So B
Same
never
way.
changes.
Yeah. And that's why, like I said, so the stuff that I'm saying assumes that you're doing this nicely, and I guess there's the lazy assumption that I'm not redoing certain things. The code that he gives, he doesn't talk about it in this way. So I'm not sure if he makes the same assumptions or not. But yeah, completely right.
That's because there's no assignment in this code, right? Only when you do assignment you change the value.
Right, but this is sort of syntactic sugar that I'm applying, right? So Torsten's point was if B was some function here, right? Then this syntactic sugar, the compiler would not be doing this without also doing something else, and that something else would be value sharing, right? Because you would not want to execute things twice. But this is simply to communicate that this is what the meaning is, and how to actually write the interpreter or compiler for this is a separate thing. Okay, so the problems. Well, we just talked about it, right? It's talking about variable values, everything very specific, everything at at the value level, and just tracking those things. So it makes the case that it's sort of overspecified, and I think it depends on what you're interested in, right? So if what you're interested in is the behavior of this in terms of probabilities, and you just want to see what this program, what the probabilities this program is inducing, then that's true. It is overspecified. because you're interested in probabilities, you're starting from probabilities, you have to first go to some values, then you have to trace all of this, come out with values, and you have to keep doing this multiple times so that you can come back with a probability distribution. Right? So what you're interested in is probabilities, then this is overspecified. There may be cases where this is sort of okay specified, or it's fine, this is the level of detail that you would want. But starting with the talk about, well, this is a probabilistic programming thing, and because it is probabilistic programming, you would be interested in what those distributions are in use, and so on and so forth. And so this is going to the second point, right? Like, what happens when you have input probabilities? I've not been given what the value of x1 is. I've been given how x1 is distributed, and I'm expected to calculate what the posterior distribution of this entire program is. What is the distribution induced by this program? Well, what would I do? I would pick first values which correspond to that. I would sample from that and then trace through all these steps and then go on, right? So that's a problem. The other problem is when we're talking about how that f is defined here, how the conditional is being defined. It's being defined as a set which is defined in terms of everything above it, whereas not everything above it is necessarily needed, right? You may only need the distribution just step before, but because it's not talking about distribution just the step before, it's like everything above it, because any of those values I can access, and so I'm going to be accessing simply talking in terms of those values, so I need all of that specified. So he makes this case and talks about it, and I think, I'm not sure, I think part of the analysis is also, so he mentions, he doesn't talk about how to extend semantics 1 when you have more types or high order functions and things like that. He does mention that elaboration is a bit not as natural, though that's coming from his perspective, right? The instruction that he gave for the denotational semantics didn't seem very natural either. But I think denotational semantics do have nice properties, and that's because they, well, we'll see some of them. They are compositional in nature and they have other properties, and I think part of that is he's able to talk about things, even though he's talking about very simple case, he's able to derive theorems which are very, very strong in talking about the general case, and he's able to do that because he's mapping it to a mathematical domain where all these properties hold, right? So he's able to do that while not making the programming language very rich. Because if you were making the programming language very rich, which is what you would need to do in operational semantics or in this kind of stuff, there would be too much detail for him to go through, right? So he's able to just piggyback on the shoulder of other giants and be able to say, okay, I'm mapping this to this domain, and I'm saying that these properties hold. I'm saying that I have a positive cone, I have all of this, I have open up space, and because I have all of that, then this is true not just for this limited language, but it would be true for this general language as well, right? So he's able to leverage that. So what does the semantics do? It focuses on the distributions, it doesn't focus on the values, and it focuses essentially on the measures induced by the various inputs and the the probability distributions were induced by the programming language, program in this program, probabilistic programming language. So he talks about, and I think part of the reason that he sort of likes this and finding it in this way, though it's quite possible, and you saw how these semantics were pretty clear even in the semantics 1, it's not really specific to semantics 2, is that the random stuff, the stochastic element, is just restricted to that one case when you're popping things from that, inference stack. And so here he looks at it in a different way, and he's like, well, okay, a deterministic program is something which, given the same input, is always given the same output. So the conditional distribution of the output given the input is just a point mass in some space. If I just have one variable, then it would be just a point mass on that real line. If I've got 10 variables, then in that 10-dimensional space, it'll be a point distribution of like, this is that particular value that I want of all these variables. It's not going to change, no matter how many times I evaluate it. A probabilistic program has non-deterministic behavior. And the important point is conditioned on the inputs, right? Because a regular deterministic program will have non-deterministic behavior if you change the inputs, essentially. But conditional on the inputs, probabilistic program has some sense of non-determinism, or the degree to which it has non-determinism is expressed by whatever the probability distributions there may be, right? So if the if the random number generator has some level of uncertainty, well, that's going to trickle down, and you will see that level of uncertainty, not always, but that can be captured, and that can result in an output which also is not a point mass. So we'll go through the same thing, and I haven't changed a lot here, because what I want to do right after this is actually go into the live demo, and we'll actually see what some of these items mean. So bear with me as I read this and sort of go through, keep this in your mind. If none of this sort of makes sense, like, well, this is the same thing as we saw previously, well, the only difference is really that we're talking probability distributions. And if it seems that it is the same thing as what you saw previously, well, perhaps there's the underlying truth which he proves as well, is that both of these are equivalent definitions. So instead of looking at values here, he just says, well, the distribution on the L value is achieved by inverting F and then using the distribution on the input. So I think this is somewhat obvious, but you may miss it. So if F is identity, right? So the distribution of x1 is everything on true, nothing on false, right? If F is the identity function, and if F is not, then the distribution of x1 is everything on false, nothing on true, right? And what are you doing? Well, you're saying, because F is not our identity, what is it doing? You have to sort of, so if F is not, and you're given, you want to figure out your space is true and false, and you're saying, well, what is the distribution of true and false? Say, okay, well, if I have false, where do I go? That must mean that the input to F was true. Okay, what is the probability in the input side that that value was true? Well, it was point mass on true, so you're sort of working backwards, and you have to invert that, right? And then you say, okay, well, that can just sort of, what did I say? Did I start with true or did I start with false? But, and then, one of the two. But if you say, if now I'm looking at x1 at false, well, when will that happen? That will only happen if the input to F was true, right? And what is the distribution of that? How much mass was associated, probability mass was there? And you just use that, right? So you have to invert F, and that's all it's talking about. Random assignment is like, okay, well, if I throw in another sort of variable, or say x1 is just a random assignment, well, it is the distribution which is induced by the random number generator. So the random number generator has some distribution, we'll just use that in place of that variable. Composition, same thing. First do this and then do the next thing. Conditional. Again, I've used in F, which is the same example before, but he talks about basically breaking it down. So what does conditional do? You've got some mass, you've got some distribution, right, on some variable. There's only one variable. You have a very, very simple case. You have some predicate based on that, right? And so I have some distribution on my original variables, which can be either true or false with some probability. Based on that, I've got the predicate, and this predicate can also be true or false with some probability now. And if it is true, to the extent that it is true, I will do S. And that S will give me some answer which is either true or false. And to the extent that this predicate is false, again going back to the input probability, that mass, I will be doing T. And that can also result in true and false. So it's just splitting, conditional simply split the probability mass distribution. You trace each path, evaluate things, and then combine them together. That's your result. And we'll see very concretely how this goes. But right before we go there, while loop is nothing else than the same thing of loop unrolling. And what happens when you unroll, what were you doing in conditional? Well, I was taking something, I was splitting probability masses, and then based on one path, I was evaluating something, and then combining them. In a while loop, I would be taking something, I would be splitting it. In one case, I would sort of stop. In the other case, I would again go back and split it again. Go back and split it again. Go back and split it again till I can escape. Right? So it keeps repeatedly splitting things out till everything is concentrated, or doesn't necessarily mean it's concentrated, but everything is just focused on what is the condition that you're interested in. Because anytime that condition is false, well, you will just do another loop. and that will repeat the same procedure. But now we'll just look at some examples. Awesome. Can you guys still hear me?
Yep.
Okay, so this is an online REPL, problems.org. I'll send the slides, I'll send this link as well. This is based in Church, and so it'll be very Listy or schemy, and a lot of parentheses, but these examples are simple, so hopefully it's not too bad. You guys can go and just play with this and see results, and you'll be able to graph things, and you'll be able to tinker around. Pretty cool with that. So I won't be introducing what the syntax looks like. I'll be going step by step and explaining what this is supposed to mean. If anything is not clear, shout out, because I think this is really the important portion that I'll make sure that you guys sort of understand here. So what I'm doing here in the first thing is simply saying that x0, the one variable that I said I was going to define my input perhaps to the program, essentially x0 is my input to the program. That input to the program is true. I'm defining it like that, right? So this entire program, and I'm doing this because of the way Church is, right? So there's no main function. It's going to, when I say run, it's just going to go through all these steps and actually just show something at the end. So this is what's happening, is saying that, okay, well, x0, and I'm going to use x0 as essentially the driver for the rest of the stuff. And I have some helpers. So I've defined what coin is. So coin with property p, this is a weighted coin. So if it's 0.5, then it's going to be true or false 50% of the time. And if it is 0.2, then it'll be true 20% of the time and false 80% of the time. Identity, just if it is passed true, then the answer is true. If it is passed false, then the answer is false. Right? Not is just going to flip these things. If it's passed true, answer will be false, false, true. So let's look at what assignment does, right? And so the idea here is to try and give you a sense of, when we talk about these probability distributions, well, how do the probability masses shape and evolve? What are we doing here? I'm defining assignment, I'm defining this as a construct, and I'm defining this so that I can call it below and I can actually plot it. But what is assignment? What is this case doing? Well, we were looking at x1 was f of something, right? That f is not of true. That's basically what I'm doing here. In this case, I can actually make this x0. So that my x0 is the one which is driving it. So I'm saying x1 is not of x0, where x0 is my input to the program. And then I'm just returning that x1, whatever that quantity is. Right? This is the extent of my program. Yeah?
Is flip a primitive here?
Flip is a primitive.
So what's the difference between flip 0.5 and coin 0.5?
It's nothing. It's flipping a coin. I just wanted to give something which is easier and not talk about flip all the time.
Okay, so under conditional where you have flip 0.5 and coin 0.5, those are equivalent?
I believe so. Let me just see. Flip. Yeah. No, flip. I think it's 0 and 1. I'm not sure. Actually, I can see. I'm just.
0 and 1 instead of true and false?
I think so. I'm not sure. Let me just run this. Yeah, it gives true and false, so it's equivalent. Yeah, so the helper is not really a helper, but it doesn't make that explicit. Okay, so we've got assignment, which is just saying x1 is some function, which is, a function which is inverting x0, and I'm returning x1. So what do you think is going to be the probability distribution of x1, of this program, of this statement? Of assignment, yeah. What is that? So we're just defining x0 here, right? So it's a point mass, and it's a point mass on just true, and that's what we should get. So let's take a look at what that looks like. So, it's on false, right? Because you have to invert. Right, so assignment, what is it doing? It's saying, so what is my probability distribution? Let's actually look at this as well. Let's start first with, let's see what this looks like. think I need that. Hold on. I think what is needed is this, yeah. Oh. Way to go. This should be closer. There we go. Right, so x0 is everything on true. It's just a point mouse on true. And so if you're looking at what simple assignment is doing, it's everything which is on false, right? Because when you take a look at the case of true and false for the assignment case, you have to work backwards, invert the function. But inverting that function, it's a not function, so the invert is also a not, right? So what is the probability that I have something in true? That would be the probability that my input, that would be the same probability that I would have if my input was false. My input, however, is a point mouse on true, so there's nothing on false. What is my probability that my output is false? Well, that would be the probability that my input was true. My input here, x0, is everything on true. Right, that's what's happening. Okay, so we can look at the next case of random assignment, right? So I've got a coin, which is a weighted coin, it's 0.5, and I'm actually even calling some function on that, but doesn't really matter, right? Just think of it as doing something stochastic here, and then I'm returning that. So what would you expect? Well, it would be the same thing as the probability distribution. So I'm doing two things here. I'm doing the random number, and I'm also applying a function on it. But what is the probability that the end result is going to be true? Well, that would be the probability that the coin is returning false, and that is a probability 0.5 because it's an even coin. What is the probability that my end result is going to be false? It's going to be what my probability is that it's going to be sort of true, and so it's going to be 50-50 roughly. Right? And so if you see that, close x0. Yeah, roughly 50-50. You can keep running it a few times. And so if you look at, so we've done assignment, we've done random assignment, right? And random assignment, as I spoke, was simply all of us doing was taking the distribution of your random thing and just putting it there. In this case, I applied a function, so you have to invert that function. Yeah.
Are you inverting it because like the function is defined as not? Like in the
No, well, it could be identity as well. I'm inverting it because when you're looking at, you're trying to find out the probability on the output. And you have a function going from input to output. And you have some distribution on the input. How are you going to figure that out? You would say, well, the probability for this thing, item there, is going to be the probability associated with whatever item was which led to this. What was that item which led to this? You have to go backwards.
So what if, like in the example, it said x1 equals f of x?
Yeah.
So what if f was identity?
Then it would just be one-to-one mapping, and so I don't need to invert anything. So it's function inversion, not Boolean inversion. Yeah.
Okay.
So then what do you mean by function inversion?
Just the inverse function. If I've got a function of x, right?
Oh.
The inverse of that function.
Oh, just going from output to
Yeah,
input.
exactly.
Oh, okay.
So in that case, would you define assignment as just x1 defined as x0? For example, if your function is identity.
Yeah. So if not wasn't there, you mean in assignment?
Yeah.
Yeah. So what do you want to do? Identity?
Yeah.
Yeah. So if you do this, let's see, the distribution on both x0 and simple assignment will be the same, right? Both are true. Does that make sense? What's happening here? Yes, no, maybe? Yeah.
Does this paper give us a means
Inverting it?
of computing the inverse
Yeah.
function over the
No. You're going into the space of what would be useful, so the answer is no. Okay, so we did random assignment. Let's look at conditional, right? So what is this conditional code doing here? okay, if B, I'm defining B as just a regular flip of true false, and if yeah, so my B is just conditioned on. I also made it as some function as well. But my B, there's nothing above it. I'm just saying that B is just a regular flip assignment on true and false. And if it is true, then I'm going to flip a coin, and if it is false, then I'm going to flip another coin, right? So what is the full distribution here? And the reason I did this was I just want to split out some of these things. So in this case, 50% of the time it's going to go to true, and within there, 50% of the time it's going to go to true again. So I've got 25% here, and 50% of the time that it went true, 50% of the time it's going to go to false. So I've got 25% on true and false right now, and we do the same thing on the false branch because that's 50% of the mass as well. And so in the end, you've got 50% true and 50% false. So, and that's what we'll see, right? And so true and false is about roughly 50%. But we can sort of shift this, right? So if you were to bias this towards, say, 0.1, it doesn't become true very often, right? It's becoming true only 10% of the time. So it's going to go into this branch only 10% of the time. But because this branch and this one is symmetric, the answer should still be 50%. Yeah.
In the paper, you said that in the examples there was only a single random variable.
Mm-hmm.
Doing the flip here and then doing the subsequent points, do those require new random variables?
Right. So in the paper, they actually deal with n number of variables. In the presentation, in the slide that I was giving, I was dealing with only single variable. Right? Here, I'm throwing it all because we can actually play around with it.
But we can think of each of the calls to flip or coin as a new random variable.
Exactly. So this should still give 50% on each, and we get roughly 50%. It can get interesting, right, if you make this 0.2. Right, so what will happen? It's going to 10% of the time it's going to go, and then 20% of the time it's going to, off that 10% is going to come into, let's make this 1 as well. So let's see what happens. I think it's still the same. Yeah, I think I'll just introduce variance here. So if I were to make this 0.8, yeah, right, so all it's doing is it's going to split up the mass. 0.9 of the mass is going to go into the false branch, 0.1 of the mass is going to go into this true branch, and in there it's going to then split out as well. And after all of these splits happen, at the end you just aggregate them all and see which one goes where. So conditions sort of split things up as we expected, and the while loop. So while loop is I've done the unrolling essentially, and that's my go function, that's my recursive function here. So what is it doing? I have some predicate which is flip 0.5. I'm calling flip, and if it is true, if I come up with something which is true, then I'm going to give naught of x, and x is whatever is passed in, and I'm passing in x0. So it'll be whatever I had defined above, right? So I defined x0 as true. So here when I come, I'll flip a coin. If it is true, I will give false. But if that coin is false, what will I do? I will repeat. I will keep repeating, right? So the only way to escape is if this thing goes false. Well, the only way to escape is coming here, and when this comes here, basically your answer is coming to be false. So your mass is getting concentrated on the false side, and what you should see is just a unit point mass on false. Yeah, okay. So, right, because it goes the first time, let's imagine, right? It flips a coin, comes up with true, okay, I do false, and I'm out. That's my loop once. I do this, and I come up with false, okay, it says try again. False, try again, false, try again, false, try again. After 10, 12, however many times, I'm going to end up running into true. And when I do, I come here, and I'm sent to false again, right? So the only way out for me here is if I go to false, and when you see the result, all the mass is just concentrated on false. There's nothing true. Because if you go true, you would still be in the loop. like how these things are happening. It's like the alternative semantics, like that we can directly talk about and reason about the effect that these statements have on probability distributions, right? So in these semantics 2, what he's talking about is saying, okay, your entire program is a function. I'm going to interpret your entire program, every statement within it, every expression within it, as a function going from a distribution to another distribution. That's it, right? And you see that from really the beginning. You see that from assignment. When I'm assigning, I'm seeing what my input distribution was and what the output distribution was. I do the random assignment. I do the composition, doing first one thing, doing the other. And it's all talking about how am I stitching these functions together, and these functions are now in the distribution space. So, and which is sort of a convenient thing, right? Because this goes into, in denotational semantics, you always pick whatever the mathematical sort of, what is your denotation, what is the mathematical domain in which you want to map these things out, right? And this could be probability distribution like here, and there's other fields where you can talk about completely different things. I can map it in terms of some abstract concept, some other discrete domain, some discrete approximation domain, and think about how these things go. But I think the power here really is to think beyond the usual semantics, right? These things can run on a computer, and if they do run on a computer, and there is a stack, then yes, you can have all these variables change. But what is the meaning of that? You still have to interpret what that variable values mean in some sense, right? So this goes straight to that interpretation. So in semantics 1, we started with saying, okay, you've got all these variables, you've got all these values associated with them. This is how we're going to represent your entire program state. And what I'm going to tell you is how step by step you go through that program's, how step by step you are going to alter this program state. But then what is the meaning of that program state, right? You still have to interpret it in some sense, but it doesn't answer that. It says, well, pick whichever way you want to interpret that space. Semantics 2 says, well, I want to interpret it in the fashion, in the way of probabilities. Okay, knowing that, what do I do? Well, you can still go back to semantics 1 and say, okay, I'm just going to run this multiple times, create a histogram of it, and then that's my answer, right? So by tweaking the variable inputs by a bunch based on whatever input distribution may be, I'm going to take the results and how these values change, and I'm going to interpret them back as probabilities. But semantics 2 shows you don't need to do that. You can directly define how each of these steps is affecting the probability. And we did some of that reasoning in our head right now, right? Like, this stuff that you're seeing here is actually executing this code every single time for 1,000 cases, right? And then plotting the result. We were able to come up with that answer in our head. And what did we do? We actually used denotational semantics without knowing about it, right? Because we were saying, okay, you have some input probability, how is this thing affecting that input probability? You sort of bypass how it's executing. And that's sort of the power. And what the paper shows, or rather states, I don't think it proves it conditioned on a whole bunch of lemmas, is that these two meanings are the same, they're equivalent. That the semantics given here with these probability distribution, the way he's defined that, is equivalent to the semantics that you would get with semantics 1. And more importantly, to test that something is same, to test the validity, if I've got two programs, I can test them on simply discrete points, and if they match on all of those discrete points, then the answer is the same. So he talks about equivalence in sort of different programs, and my interpretation of that, which guys correct me here, but my interpretation, the way I read that was, if I am executing that program, if I've got sort of two programs, I only need to match that up on all the discrete inputs. So if my code evaluation is the same for all the discrete inputs, then it is also the same for all the probability distribution induced from it, essentially. So I've got program 1, yeah?
Sorry, when you say discrete inputs, do you mean the input to the random assignments or the input to the program?
Input to the program.
So we've got some variables that are assigned from probability distributions. We're leaving those alone. We're still getting whatever their distribution is.
Yeah. So he doesn't actually mention that very clearly, because he actually gives an informal description based on just the fact that any probability distribution can be broken up into a discrete and continuous component. He gives this reasoning on the discrete component by matching it up. And then he says, well, reality is a bit more complicated. It has this and this and this, and also has continuous distribution. But regardless, this theorem stands. Right? And the reason this theorem stands is because of the entire notation that he talks about creating lattices in Banach spaces, and I'm using that to say that they will be least upper bound and calculating all of that stuff.
Right. But the theorem itself, is it saying if I have a program S and a program T, and I give them both true as their input?
If S and T are programs such that the probability distribution induced by this is the same as this one, for all point masses, then S is the same as T.
Okay, where mu here is the input to
Mu is the measure on the inputs.
on the measure of random assignments?
No, it doesn't. I don't think it includes that. It's then keeping the random number generators sort of the same.
But mu is not the random number generator's measure. It's something else.
It is the distribution on the inputs that you have.
Right, sorry. I guess my question is really about what the word inputs mean.
What does the word in?
Does that mean the random assignments, or does that mean what I'm feeding into the program
I think what you're feeding into the program.
as a discrete value?
Well, that can be continuous as well. So he only talks about some finite domain on which this is there, some x, but he says that this is sort of a simplification. So this can range over, let me just find the section here. Yeah, so lovely bit of notation. But actually it was, yes. So what is mu? Maps distributions on x and m n, right? So x is all your set of variables, if I've got that right. Because, yeah, program variables x1 to xn.
Okay, so it is over the random assignments as well.
Well, the random assignments are, what are you assigning it to? It is a variable. Right. So it would be over across all of those variables. Yeah.
So we can think of this as a program that takes an input, but it has some amount of non-variables and then you evaluate it.
Sure, you could interpret it as you've got these variables and there's some perhaps prior probability or leading towards this, and then you start executing all of these steps.
And we're going to fix, for two given programs S and T, we're going to fix our probability distributions such that they are point masses over all of these random variables.
Over all combinations. And if that's true, then
Well,
these
so for one evaluation, one measure, where we've got point masses for each of the random variables. So
Mhm.
assign them all to true, assign them all to true, see what comes out. It's false or relative, and they match. Assign all of these to true, and this one to false.
Yeah, try all
See what
combinations.
comes out,
Yeah.
if they match.
yeah.
And then the theorem is, if this is true for all those discrete cases,
Then it's true for the entire all sort of probability distributions and things like that these programs are truly equivalent. Again, doesn't give you anything useful because you can't actually try all of the combinations.
if you have more than 10 variables.
Yeah, even in tech variables, it depends on what they're ranging on, right? So, but yeah. Okay. Any sort of questions? Any discussions? Because I would love to talk about various aspects here, but depends on where sort of the interest is. And we can talk about something completely sort of unrelated and saying, okay, assuming or knowing this that we know now, perhaps you can talk about a probabilistic program or different stuff. Or we can just call it tonight. Yeah. Yeah.
Would it be correct to say that if you had like the distribution for a function,
Uh-huh.
you could replace that function with that distribution?
Yeah, it's equivalent. Well, in terms of the meaning, in terms of the denotational semantics, so in terms of how you would interpret or evaluate the probabilities, yes, you could. That may not be the case if you're actually writing a compiler, and which requires certain other technical detail, and if you would want to ensure that computationally both of those are equivalent, right? That it's not doing, like if your function has some other effect that it's happening, your probability distribution perhaps not having that effect. Yeah.
Can you motivate again why this theorem is important?
Why this theorem is important?
Yeah.
There's no motivation. I think this is, well, it's important in the sense that he's showing these two different ways to look at it, and then he's concretely saying that there's a way to connect these two.
So like the S and the T are actually two different.
Sorry, there's two different programs. There are two things that he does. One of which is actually drawing the connection between denotational, semantics 2 and semantics 1.
So like
you-
S is different semantics of T.
No. I was confused as to which connection which theorem you were talking about. But there are a couple.
Which one you just
Right. So the implication that if it's true on some finite set or on these discrete points, I think the implication or the real goodness here would be, if I want to show equivalence or if I want to show reliance of some equivalence, I can simply consider the discrete point mass case, and I would be okay. Right? I don't need to consider the continuous case because that will follow through if the prerequisites for this theorem hold.
I see seems there was some confusion around this at this point in time, that's why this was shown, or is this some
I think this was one of the first times where they were one of the earlier times where they were truly interpreting it as saying, okay, well, it's a random number generator, there's a probability distribution associated with it, and well, we should be thinking about what does that mean, right? You have to consider this came before any inference or any of that came about, right? So saying that I can write a program and have that compiler or the inference engine behind it reason backwards wasn't a notion. Right? So people were not thinking about that. People had introduced random numbers. Why? Because they were like, well, I need to be able to vary something. I need some way to be able to do that. Right? So the motivation in Fortran, why do you have random numbers?
so like going back to the theorem.
Yeah.
If you had one word that you would like to underline in the theorem, which one would it be? Would it be discrete? Would it be equal? Would it be for all point masses?
Well, I would say for all point masses, and that I'm showing that these two programs are equivalent. So for me to know unambiguously what is the meaning of a program, or what is a program, I only need to consider all the cases, and there are lots, but mathematically that's easy, of the value of this, of the distribution induced by this, and distribution induced by this on point masses, and that's good. Okay, so
I was just going to say, in general, having that type of equational reasoning in our toolbox is a really powerful advantage. If I can show that some simpler program is equivalent to some more complicated and slower program, that's a really powerful thing.
yeah. Awesome. So this ProbMods play space, if you want to tinker around, there is also, if you go to the page, a full reference of just reference guide, and there's some like examples as well. If you dig around in the probabilistic programming repository, which actually we have gone through some exercises that actually I'm not sure if I actually committed those yet, but I'll probably do that. I'll share all of this stuff, all the links, and put that in the slides. Thank you so much.